the message that I would like to give you is that I'm working in the area of material science, so I'm not working in the area of computing science. I'm dealing with materials, with the semiconductors, the ingredients that feed in some way the computers and all the devices that we are using for computing. But I work in this part more on the semiconductors, and I will speak a little bit about new materials, especially what I used to say green electronics, because as I will present later, we are facing a lot of problems concerning pollution, especially related to the conventional electronics that we are using, and for some new applications, especially, for example, the Internet of Things and things related to that, we need to use other materials because, or if you want, sustainable materials. So this is the main message. Of course, the idea is not using, for example, paper electronics to build a microprocessor, but for intelligent packaging, maybe I don't need to use a silicon-based microchip. I can use alternative materials because they work. The performances are quite enough. So the title is The Future of Green Electronics. And this is not working. Why? Okay, in our laboratory we have a strategy, and since we work with materials, we are looking, as I mentioned previously, with abundant and non-toxic materials. This is one of the keys. The second part is, since we need to process the materials, we need to use this type of materials to build the devices, we are also looking for green technologies, which means that we are looking for simple and low energy process. So in terms of just for you to have an idea about the main areas we have in our laboratory, it was already mentioned, I am coming from Universidade Nova de Lisboa, from Faculty of Science and Technology. The campus is located on the other side of the river in Lisbon, in Caparica, and we have these 5 main areas. We have transparent electronics and paper electronics, and I will talk a little bit about these 2 today because also they are more related with this part of electronics. Also, we have an area on electrochemical devices, biosensors and microfluidics, and also nanoplasmonics. And this last area on nanoplasmonics is more related to solar cells. Our group starts with amorphous silicon for making photovoltaic devices, solar cells, to convert the radiation into energy. And now, since also the materials is a little bit already exploited, now what we are looking is to use new architectures in terms of the device, the solar cell construction, and using, for example, this approach of nanoplasmonics to try to absorb, to collect more radiation into the solar cell, and in that way to increase the power efficiency. So this is where we are. So here is the Tagus River. This is Lisbon in this part. This here on the left side is the ocean, and this is our campus. So we have here the majority of all the engineering degrees. And our laboratories are located here in these 2 main buildings here, and the material science department is here. So our laboratories, in fact, we have laboratories in 3 main buildings, but they are more or less close to each other. So some facilities, we are well equipped in terms of microelectronic laboratories. We have 2 clean rooms, so we are able to produce all these microelectronics and all these type of devices up to sizes of 2 micrometers. This is the main resolution we have that depends on the mask aligners we are using. And besides that, also we are well equipped, not only in terms of production facilities, so we are able to produce the materials, to develop new materials, and this is quite important. Also, we are very well equipped in terms of characterization facilities because we produce materials and we need to characterize not only the material itself, but also the devices. So the characterization tools we have are not only for materials, but also for device applications. So we have a lot of physical techniques, mainly because we work a lot on thin films, so we use mainly sputtering. The sputtering technology. Also here something is not working. And, okay, sorry. Also, we built, 8 years ago, I got my first advanced grant from ERC, and part of the money was to acquire this nanofabrication tool. In fact, it's a scanning electron microscope, but we have an ion gun, so we can deposit, we can remove, we can fabricate devices at the nanoscale, not only C. And this is more or less what we have in terms of our main infrastructure. So I will speak a little bit, not a little bit fast about these two main areas, because I prepared already the presentation on transparent electronics, what it is, and after that on paper electronics. And at the end, I will just summarize a little bit in terms of the future, not only in computing, but also in terms of thin films, the other area, because I'm not talking about silicon, so crystalline silicon, that is the king for the microelectronics and also the microprocessors, and I will focus a little bit in these two main areas. So maybe we know this type of, or you saw in the past this movie from Steven Spielberg, and this is Tom Cruise. It was released in 2004, where Tom Cruise manipulated a lot of information using large screens, transparent screens. Of course, this at that time was not a reality, it was science fiction, but sometimes this is quite important for us as scientists because we try to see these type of things and we think also this should be possible, and we try to exploit and to push a lot the material properties and try to build these type of things. And in fact, today this is not, maybe it's not so nice to have a transparent computer, a screen, a transparent screen, but of course, this is already available, and we have a lot of devices that are using this technology, especially mobile phones, in the area, for example, for OLEDs. In terms of display applications, as you know, a display, we have a matrix, an active matrix. We have pixels. Each pixel is driven by a TFT, a thin film transistor, and actually these thin film transistors are based on amorphosilicon. So now we replace all these amorphosilicon by new materials, metal oxides. And for example, we have now a lot of devices, especially mobile phones, with OLED technology, and for OLED, amorphosilicon TFTs are not good because they don't supply enough current to shine, to open the OLED. So this is a technology that is already in place. In fact, for example, we have patents with Samsung in this area of the architecture, for example, of these thin film transistors. So in fact, transparent electronics is very easy, just the combination of optical transparency with electrical conductivity, because as you know, the metals, they present a very high conductivity, electrical conductivity, but they are not transparent, they are opaque. If you look, for example, for the glasses we have in our windows, they are transparent, but they are not conducting. So in principle, these two properties they don't like each other because they are quite opposite. If I want to have something with a very high conductivity, I cannot have simultaneously a very high transparency. And in fact, we can do this. And for example, this was a prototype that we built in our laboratory, where we have, for example, this is the logo of Faculdade de Ciências e Tecnologia with some small LEDs. And here is a piece of glass with some materials there embedded that are transparent, but simultaneously these materials they present a very high conductivity. So we combine in this way, in this type of materials, mainly metal oxides like zinc oxide, indium oxide, and tin oxide, we are able, and with some dopants, we are able to produce a material that is simultaneously transparent and simultaneously present a very high conductivity. And also just for you to have an idea about how important are mobile phones or mobile things or around our society, this was, maybe you know these pictures, this was the election of the previous Pope, the Pope Benedict in 2005, where you can see some few devices, and more recently for the Pope, the Pope Francis election in 2013, you can see these are not candles. These are all mobile phones. Just for you to see how important are displays in our life. And again, for example, if we compare or we see the evolution in terms of mobile phones, for example, the previous mobile phones, they were quite big and heavy, but look now, they are still big. What is going on? And what we see is that for example, today, the mobile phones that we are using, they are limited to the size of the display. So the display now governs, if you want, the size of the mobile phone, because the previous ones, they were also big, but with a very small display. But here, the size is more or less the same, but the main area is occupied by the display. And also other examples, for example, now we can have not posters or paper, cellulose paper with some information, with static information, but we can cover our walls with some displays, interactive and touchscreen displays. And also, for example, this is a picture of the Incheon airport in Seoul, where, for example, besides having a lot of displays, now they are using a lot of these new curved sensors, the displays. And also we have displays that can be rollable, flexible, and conformable. So we can roll our television, for example. Also, we like to have big televisions. We can roll up our television just to avoid some space, or if you want to rearrange the furniture in our home, but this is quite possible. This is a video. I'm not sure if it will work. This has already some years, but this is a huge display based on OLEDs, and works simultaneously as a window, but also as a display. So we can cover all the windows we have around with displays. Why? Because you are using these transparent materials and simultaneously with a high conductivity. For advertising, marketing, and also maybe in the future you can have buses like this one. This is not yet real, but maybe in the future, yes. And this is possible because we are using this new type of materials or metal oxide semiconductors. And in fact, we used to say that we are in the presence of a new class of electronic materials. So we are not restricted to silicon, to gallium arsenide, to germanium. We can work with copper oxide, zinc oxide, gallium oxide, indium oxide, tin oxide, and also not work with the materials alone, but also we can combine indium oxide with zinc oxide, with gallium oxide, and exploit different properties in a single material. And this is quite important. Not possible, for example, with silicon. And one of the first materials was zinc oxide. And in fact, our first transparent transistors have been produced using zinc oxide. And again, this is a biocompatible material. For example, when we go to the beach, we need to protect our skin from the UV radiation. And if you take a look about the composition of the cream, you will see that the basis is on zinc oxide, because zinc oxide is a wide bandgap semiconductor, absorbs UV screen, and when we put the screen over our skin, works like a filter and protects and absorbs the UV from the sun. Why these materials are so attractive, and even in a short period of time, we have already available products in the market, because they present a low cost, they are biocompatible, they are recyclable, the technology is green, that I will show after, and also at the end, they present a superior electrical performance. And this sometimes is not so easy, or is not common to have all these advantages when we change from one technology to another one. Because, for example, if I change some material, if I want, for example, to decrease the price of this remote control, or to improve the performances, sometimes increased performance is not simultaneously, I cannot have a reduction in terms of the price. Usually this is not like that. But here it is, so also these materials are quite attractive due to this. So I don't want to go too much in details about these, how they work, but for example, just for you to have an idea. And of course, one of the main applications of these materials is for thin film transistors and for display applications. But all the displays we are using, they are based on this type of technology, TFTs. The available technologies we have now in place are oxides, amorphosilicon, polysilicon, and organics. But for example, if we compare the properties of the TFTs here, for example, and if I pick one, which is, works like a figure of merit of TFTs, which is the mobility, we can see that for oxides, we can reach mobilities of the order of 100 square centimeters per volt per second. For example, amorphosilicon is limited to 1, because the material is amorphous, presents some defects. Polysilicon also, we can reach values of 100, but since it is not an homogeneous material, has different crystals. For example, if I'm looking for large televisions, for example, large displays, I cannot have an uniformity over a large area, so this is quite good, maybe, for example, for mobile phones, where the display is not so high. And again, the organics, and they are performing well for some applications, but again, in terms of the application for TFTs for the display area, also the mobility is quite low. For example, the maximum values are quite similar to the ones of amorphosilicon. And also, today, the material that is already adopted by the industry is based on this GIZO, is gallium oxide, indium oxide, and zinc oxide. Is a combination of different materials because, for example, indium increases the mobility, gallium decreases, for example, the carrier concentration, and I can achieve a higher modulation in terms of the channel, because the TFT works like a MOSFET, is a field effect transistor. In terms of performance or working is quite similar. And here are the main advantages. A high resolution, because we are dealing with transparent transistors, so I'm not limited to this dead area that I have, for example, with amorphosilicon. They present a high mobility, also a higher on-off ratio, low power consumption, and also low noise, especially if we are talking about touch screen displays. So they present a lot of advantages. We produce a lot. We start this area more or less at the beginning, so we are pioneers more or less in the world. So that's why also we are famous and about this work. But for example, if you work with industry, there are two things that are quite important. One is stability, and the other one is reproducibility. For example, I can build in my lab a device with a huge mobility, but after that, if I cannot produce 100 similar devices with the same mobility, this is not good. So maybe it's quite good for publish a paper, but it's not good in terms of industry. For example, stability is quite important, and here we have just a device, a TFT. This is a typical transfer characteristic, the IV curve. And even after 10 months, you see the device, the curve, the electrical performance is exactly the same. So it seems or it means that the materials and the devices are stable. The second thing is reproducibility, and here we have, again, a similar IV characteristic, and here we have 168 transistors, or 168 curves. And as you can see, they are the same. So if I'm building a huge screen or a huge display, the TFT in this corner and the other TFT on the other corner, they should have the same electrical performances. But oxide TFTs are much more than transparency. Of course, we are not only looking for active matrices. As I mentioned, we are in the presence of a new class of electronic materials, and we can exploit also these materials for other applications, for electronics, for example. Some examples we are able to perform, and this was done in our laboratory, some CMOS inverters on pen foil, because I didn't mention at the beginning, but we produce these films, these devices at room temperature, so we are able to produce devices, transistors on a plastic foil or on a sheet of paper. Other examples of zinc tin oxide, other type of circuits, for example, a ring oscillator on pen, which is a polymer, and also other circuits that we can exploit using this type of materials and devices. But we are facing some issues, for example, especially, for example, the Internet of Things, and the new challenges are approaching. And, for example, if we want to reach this type of technology or application, we need to have other things. Especially, we need to build devices ultra-cheap and disposable, with seamless integration, with power management, especially ultra-low power electronics, and also efficient wireless communication. So I'm not talking just, this is not for microprocessors or for computing, but for other type of applications. So sometimes, again, if I want to reduce the price of a product, I have two ways: reduce the price of the material or reduce the price of the technology. Reduce the price of the material is a little bit complicated, because if I want to purchase gold, the gold has a global price, so I cannot, the price is there, so it's more difficult to change. But I can change the processing technology that I'm using. And for example, in the previous results, the main technology we are using is based on physical techniques, sputtering, where we have some systems with vacuum, with gases, and we are able to produce thin films using a physical deposition technique. But again, for example, if I'm looking for a reduction in terms of costs, and again, I cannot touch the price of the material because it's there, it's the price that I need to pay, I'm able to reduce, for example, the technology that I'm using for producing the same material or devices. And for example, if I compare a microelectronic process, and this is typical, for example, for CMOS technology, where I need to use vacuum and photolithography, they are quite expensive, and also I need to use a lot of steps. But for example, if I change from a vacuum process to a solution-based process or for a printing process, I can reduce the costs of 64%. Why? Because I'm not using vacuum systems, and also I'm not using photolithography. 1 liter of photoresist is quite expensive. So I don't need to use these systems and these materials, and I'm able to reduce the price for more than 64%. So we start to work also not using a physical technique, a sputtering, a process. I don't know if you are familiar, maybe I don't know if you are not familiar, but also I can release the presentation, and also if you have some doubts, you can send me an email, and I'm able to explain you. But for example, nowadays what we are looking, and this is for solution process, we are making the same materials and also producing the same devices using just a very small lab with some reagents and promoting some chemical reactions. So it's very, very easy. And what we observed in the last years, for example, here I plot these are some TFTs based on these materials, and these materials here, they are the semiconductors. So this is like the silicon, indium zinc oxide, indium gallium zinc oxide, zinc tin oxide, and so on. What we observe in the last years is that here I plot the temperature, the mobility, and since this is the technology is based on chemistry, usually in order to promote all the reactions among these different reagents, I need to add energy. And usually the type of energy is by heating. And for example, here, this is why temperature is important. I plot the temperature over the years, but what we have been observed is a drastically reduced value of the temperature. For example, the previous results, they need to heat the materials up to 600 degrees, for example, if this is not compatible with the use of a plastic substrate. But nowadays, we are able to produce these devices at temperatures around 150 degrees, and also in some cases even lower, 100 degrees. So we are able to promote all these reactions because instead of using only temperature, we can add, for example, UV radiation, and try to add to the system other sources of energy in order to promote all these chemical reactions and at the end achieve the same result. And again, the mobility, which is, as I mentioned, the figure of merit of these devices. So we observe a decrease in terms of the final processing temperature, and simultaneously we observe an increase in terms of the electrical performance. So, for example, even with some results, for example, this is a very famous group from Northwestern University. They achieved mobilities of 100 using just some liquids and promoting only this type of chemical reactions. So also we build the same. This is just some examples to show you that we are able to produce these transistors using this solution approach. I'm not going to details. Also in plastics, we are able to produce all these on plastics. So this is also more or less what I would like to tell you in terms of transparent electronics. So one of the main areas of applications is for displays, for substituting the current amorphous silicon TFTs by these oxide TFTs. Now I will talk a little bit about paper electronics. And again, not at this time with Spielberg. Sorry. The remote controller is not working with my computer. I don't know what is. This is a video. And I need to control this. Again, we have been inspired not by Spielberg, but by Harry Potter, where, for example, it was possible to have, of course, this is science fiction, but to have images on these newspapers and on these type of things. And again, why not try to use other materials like paper to produce electronics? And again, this is what we are facing today. We are producing what is called high-tech trash, because all the electronics that we are using today and in the past, we are not able to recycle these electronics because it's quite complicated, and in some cases, if it, in terms of economically, is not relevant to make this type of to make this type of recycling. So, but this is not the best way for making recycling. Also, this is not the best way to perform waste selection. Can we change this? And also, maybe you know this, but for example, if we take a look on the international electronic waste shipments, this is what is happening today. So we are not solving this problem. We are putting this problem out of our doors, and we are exporting these electronic waste to some countries in Africa, India, and in China. And of course, this is not sustainable. And also, besides this, we are also facing another issue, which is the pollution with plastics. Our oceans are facing, for example, in, I guess, 10 or 30 years from now, if we will use the same rate for putting plastics into the oceans, we will have more plastics than fish in the near future. And of course, this is not sustainable, and also we need to avoid these type of things. Also, for you to have an idea, we, as Earth, we dump, in average, 8 million of tons of plastic into the ocean each year. So this is a huge, this is a crime. Even now the European Commission is looking, and even in Portugal we have a lot of work and also publicity just pointing out these factors and also alerting persons to try to use not plastic, but other materials, especially coming from renewable sources. Because if you remember, plastics, they have only 70 years. They have been invented at 70 years. And they already produce all these negative impacts in our world. So, this is also why we think that it's necessary to use alternative materials, especially materials coming from renewable sources, sustainable materials. And again, this is why we are also using paper as a new electronic materials. If you want to see some work, for example, this is a nice review that appeared 2 years ago, I guess, on Chemical Reviews, where it is possible to, the title is Wood-Derived Materials for Green Electronics, Biological Devices, and Energy Applications, where you can use a lot of cellulose-based materials for this type of applications. Also, we published this already this year, a review paper from our group, multifunctional cellulose paper for light harvesting and smart sensing applications. And also, since now we have a lot of work on graphene, even it is possible to use a very low-cost technology based on CO2 laser to produce graphene from the wood. Okay, so this is a very nice work done by Professor Tur in Rice University. So we have a lot of different possibilities, and of course, targeting other applications. The idea here is not replace something. I don't want to replace, again, the oxide-based materials for a microprocessor or the paper-based materials and devices for a microprocessor, but there are applications where it is much better and easier to use these alternative technologies. So in 2008, we built the first paper transistor. So all the trend that we are facing today is to use or to substitute cellulose material or paper office by an electronic component. That's why there is e-paper. But we do the other way around. We want to use paper, again, the cellulose-based material as an electronic component. And we switch the E from the left to the right side. So we don't work on e-paper, but we work on paper-y. And this is very easy. The paper transistors works, the paper itself works as two functions. The physical support works like the substrate, because it's like the paper. I need to write something, and the paper is the substrate for the ink or for the graphite, and also has an active function. And this is a cross-section of the first paper transistor we produced. We start from a thin of paper, office paper, and we built on both sides of the paper. This is like making a photocopy on both sides. We deposit a gate on the other side of the semiconductor, and we built the transistor. And it works. So this is the IV curve, again. Of course, the leakage current, the off current is not so low as on the other cases, because paper, and this particular paper was not optimized to work like the dielectric material of the field effect transistor. Now we are able to reduce these values much lower, because what is important is the orders of magnitude that I can modulate the conductance over the semiconductor region. Okay, and why we are using paper? Because it's the most abundant biopolymer and environmentally friendly. It's flexible and unbreakable, and for some applications this is quite important. I'm looking for the weight is important, also flexibility. The cost is low, is the lightest known material. The technology is very well established. For example, we have one of the best industries in the world. The name is Navigator, and they are producing, for example, they are able to produce today, or the technology is able to produce office paper at a velocity of 100 kilometers per hour of paper. So we don't need to invent again the wheel. It is already there. The paper has good dielectric properties, is ubiquitous. For example, if we want to produce some devices based on paper or some applications using this type of technology, it's quite important. If the raw material is available everywhere, and it is the case of paper, and at the end is recyclable. We work in paper on two different ways, at the micro and nano scale. For example, here we have two SEM images. This is the 3D cellulose fibers, this 3D network. The only difference, this is office paper, this is nano paper, so the difference is the scale. Here we have 100 micrometers, here 100 nanometers. Of course, in that case, the paper is transparent because the fibers, the dimensions are at the nanoscale. They present good properties in terms of structural properties. The cellulose is a crystalline material. In terms of optical properties, office paper, as you know, is not transparent, is opaque. But again, nano paper, since the fibers are quite small, we don't have interaction of the visible light with the fibers, and the paper is transparent. So here we have the transmittance as a function of wavelength, and as you can see, around 400 and 700 nanometers, the transmittance is near 60%. This is how it looks like, and this is very easy, because also we like to have different alternatives, not only to work with vegetal cellulose, but also we are able to work with bacterial cellulose. And I don't know if you know, but vinegar has inside some bacteria, and they are not pathogenic, so they perform quite well. And I like, for example, to add vinegar in our salads. And this bacteria produces this network of nanocellulose as a way to defense. And for example, if we have a specific culture with all the ingredients, we are able to produce also nanopaper or paper using not the trees, but using a solution based on vinegar. And for example, if you compare both technologies, for example, for getting cellulose from the trees, we need to wait in average between 4 and 5 years to have a pinus or an eucalyptus tree with the exact dimension and to extract from the wood cellulose. And for example, if I'm using another technology, this Acetobacter bacteria, I just need to wait between 2 to 3 days to have, again, a sheet of paper. And in that case, it's transparent paper, because also we work a lot on transparent electronics. In that way, we combine paper electronics with transparent electronics, because also we are using transparent paper for electronics. Now, just a flash of different applications that we have done on papertronics in our laboratory, on solar cells, electrochromic devices. For you to have a taste, we work a lot on biosensors, especially for glucose testing, and the idea is to use a paper strip and to develop some colorimetric diagnostic tests like the pregnant test. So we don't need to use all this electronic for making a test, and also in that way the cost is much lower and we can afford much persons. And also we are using the concept of lab on paper. So we print the new printers from Xerox. They have inside the ink is wax. We print wax over the paper. If I put the paper on a hot plate, the wax diffuses over the paper, over the thickness of the paper, and I will have hydrophobic barriers, so I can have microfluidic inside the paper. So here are just some examples for, these are real examples for glucose, where I have the paper covered by the wax, here is protected, and I have just the channel, the microfluidic channel over there. And so at the end, I will have some, in that case, are some enzymatic reactions, and I will have a different color, and the color is function of the concentration of glucose that I put here. So they are quite low cost, and also at the end, I just burn this type of devices. I don't have problems with contamination, and also plastics and whatever. So here again, other examples, some more sophisticated, but this is just a question of printing, and also we also can avoid this coffee ring effect, and we can, for example, these are real colors as a function of a different concentration of glucose. Also solar cells, and we start, for example, with the name is Tetra Solar. We start with the Tetra Pak material, has already an aluminum foil that works like the electrode for one of the contacts of the solar cell. And we build we perform solar cells on these Tetra Pak packagings, also on paper, also on this bacterial substrate, and we got a very huge efficiency because, again, we need to reduce a lot the temperatures for building these devices in these temperature-sensitive substrates. And this is more or less what we want to do. This is our dream, to have a lot of different devices. Some of them have been already done, but using paper. But I just would like to finalize with something that is maybe more related to what you are discussing here during this summer school. I don't know if we will have a death of the Moore law or not. But this is the trend. And as you know, for the Moore law, this is an empirical law, but nevertheless has more than around 65 years. It was performed by someone from Intel, I guess. And what this law claims is that between 18 or 24 mouse, the duplication or we are able to duplicate or to miniaturize half all the components that we are building in a microprocessor in terms of the size. But of course, this has limits, physical limits, because at the end we cannot extrapolate the Moore law until cutting the atom or making a mouse or a microprocessor inside a single atom. So there are some physical limits that are imposing some restrictions to this law. Nevertheless, and maybe you know this much better than myself, the main idea that we have, or we are facing today, and the researchers in this area, is to try to exactly to avoid the problem of the Moore law, the Moore law, and since we want to have more functions and to have more velocity and more capacity within the microprocessors and the memories, the trend now, as you know, is to combine the logic and the memory inside the same chip. Because until now, the processor and the memory, they have been separated. And now, just in order to reduce space and increase the integration, the idea is to have the logic and the memory in the same device. So this is more or less the trend. And I'm not working with silicon, I'm not working in this area in particular, but I'm working a lot on thin films. And I just got now my second ERC. It's not yet running. I'm dealing now with the contract. But it is something similar. For example, what I propose in this project, for example, the name is DigiSmart. Usually, we have, for making an integrated circuit, I have different devices. I integrate these devices to perform a function. And what I propose to do is not this, is to have a single device, is to add multifunctionality to one device to perform different functions. So instead of having an integrated circuit, I will have an integrated function. So this is more or less the idea of and was well accepted by the European Commission, but also is something similar to the trend in terms of the conventional microelectronics. Is try to combine, to add functions in a more space, to combine things. So this is what I'm proposing to do in terms, not only in terms of materials, but also in terms of devices, where I can have a transistor that simultaneously works like a field effect device, but also changes the color. So I can have simultaneously the pixel and the transistor in one single device, or I can have a memory and a transistor in the same device. The single transistor works simultaneously as a memory and as a transistor or a battery. So this is more or less what I'm proposing to do in terms of device and also in terms of materials. I'm proposing again to use new technologies for using a maskless approaching. So I'm not using the clean room. I'm using a lot of different lasers to produce all these type of materials and at the end, these applications. Just an example to show, these are some preliminary results where this is a device that simultaneously has a color. So I can use this in a display or whatever, is a color display if you want, but also has some power inside. Is an electrochemical based device where I can storage some power and it can work like a battery. Simultaneously is a color sensor and again has some power that I can use to power something around, some electronics or not. And this is what I would like, the message that I would like to transmit. This is our group. We want to use very much this sentence. If you want to go fast, go alone. If you want to go far, go together. And we prefer to go together. And of course, it is important not only the team, essential, the persons, of course, but also we need to have some euros. And I would like to acknowledge, of course, the national funds, quite important, but the principal are the European funds, especially from the ERC office, and also other H2020. These are just some running projects that we have now running in our laboratory. And I would like, finally, I would like to thank you for your attention.
So
if you have any doubts, even before the dinner.
So I know it's been a long day, but let's try to keep it to just a few questions.
Thank you for the presentation. I was curious, normal paper has a reduced lifetime so the degradation in nature has a reduced lifetime when comparing with plastic. I was wondering if the paper E as an increased degradation lifetime. It's not
Also,
the right
I didn't
word,
mention, but for example, again, I used to say to my students, we don't have bad materials. Depends always on the type of applications. And the trashes in our laboratory, in my labs, are always empty because we will use everything, all the results that we are making, even if it is a failure. We try to change the failure in a success. For example, the glue from the Post-it, it was a failure. Yeah. And it was during, okay, but in terms of the paper, and coming back to your question, these are things that are disposable. The maximum period of time is no longer than 6 months because we are targeting intelligent packaging. So nowadays we are looking, as everyone is, for example, now, okay, of course, we still go to the supermarket, we go to shopping, but again, the trend in terms of the new generation is to acquire everything online. So we will observe now an increase in terms of transport for packaging. And again, we still to have some intelligence in this packaging, and this is quite important. And I will not put a microprocessor using the microelectronic conventional technology on the packaging, because they steal for years and the package is just for weeks or months. These are disposable things.
Okay, thank you.
So this degradation issues is not an issue.
Okay, thank you.
Hello, and thank you for the quick but very interesting talk. My name is Alex. I wanted to ask about the glucose sensing paper. Mm-hmm. I've been following a little bit, and I would like for you to comment on the current bottlenecks of the technology, where the problems are arising the most. Is it the enzymes, immobilizing the enzymes, the diffusion?
No, this is very easy because, for example, the roughness of paper is quite high. Is tens of micrometers, so the immobilization of the enzymes is just a way of pipette putting there the solutions. It's not a problem. But again, the cost of the sensors, and in particular the glucose sensors, is the enzyme. And for example, now I didn't show now the results, but we are producing the same sensors without enzyme. Because, for example, we are using gold nanoparticles. Again, the quantity is quite small, it's not expensive. But glucose, for example, if I want to produce gold nanoparticles or silver nanoparticles, I can exploit this plasmonic effect. I don't know if you know, but a solution with gold nanoparticles, the solution is red. And conventional gold is yellow. Because we have at the nanoscale these effects, the plasmonic effect. And the way I will produce the gold nanoparticles is the precursors is a salt using gold. And glucose is, by lucky, a reducing agent of this salt. So I can use the glucose that I want to detect. In the presence of this salt, I will produce gold nanoparticles. And these gold nanoparticles, the size is function of the glucose concentration. So we have already this, is not yet published, but for example, a student finished the master. I can use a glucose sensor, red or blue, depending on the amount of glucose, on the concentration of glucose, and without enzymes. Because glucose itself promotes this chemical reaction of the precursor of the nanoparticles, and I will have red nanoparticles or blue, depends on the size.
Thank you so much.
I don't know how many questions I have, but I will start talking and then probably the question will pop up. So it's really interesting technology. As a Portuguese, I follow up your success, so congratulations. My question is really about, because we look at your technology and your team technology and we see a lot of instant applications in the market. Mm-hmm. So my first question is, what is the current status of technology transfer from investigation to the market, and how you operate it, if some of these technologies are already there in products, or if you are working with companies, or if we have ideas, do we need to pay you patents to use this technology? And the second one related with the paper, how much in terms of cost and production, like Navigator you talk about, how far as we go in this technology to replace traditional paper, like you said, for packaging, and instead of printing, you could have this electronic paper just to print the address, and then this will self-destroy. So the two questions.
Yeah. I present today two main technologies, transparent electronics and paper electronics. For the transparent electronics, maybe is more incremental. And this is why it was easier, because we just substitute amorphous silicon by other materials. And in that case, for example, we have a patent with Samsung, and we have already some products in the market. So this was a little bit easier. In terms of paper electronics, this is disruptive. And for example, when we are making something that is completely new, sometimes it's difficult to see or realize where I can use it or what type of thing I will be able to replace. So nevertheless, we are, besides the European projects with several companies in Europe, we have now, in this moment, a huge project. It's a contract, it's not a project. In fact, it's a contract with Imprensa Nacional Casa da Moeda. We are building two projects with them related on paper technology. I cannot give too much details, but Imprensa Nacional Casa da Moeda is quite interested, and we are running now two projects directly, and is nearly a little bit less than €1 million. Is a huge project, especially if we take into account the average of the FCT projects. Yeah. Okay, but we are a little bit far. Okay, it depends. We cannot make everything. We are professors, we teach, we perform research as a professor at university, but we still don't have these type of infrastructures in place in our universities. We are far from them. For example, we are still far. We are far in this part, in the exploitation of the results, because we have a lot of results, we have a lot of good technology. That's why we, for example, in my lab, we got already 5 ERCs. Maybe in Portugal, if you count in the labs, this is unique. But we don't have in place the other parts, like at MIT, Stanford, or the other universities, to have persons or these offices just to transport these technologies and these ideas to the market. For example, how we start to work with Samsung, because we publish a paper, and during a conference, there were some Korean guys around. Not because our patent office in Portugal contacts Samsung and tell them, okay, we have here something that maybe is interesting. We are still far in this part, but we are going there. And it's more difficult. It's more easy to build transistors in the lab.
Thanks a lot. I'll be really quick. I will ask you about next steps. So you are working on a technology that is disposable and green. The question is about its sustainability and scalability, because what if we cannot just cut all the trees in the world and make paper chips?
Sure.
Have you done any, or it's not your job, but do you have any idea about its scalability?
When the first paper transistor was released, even I got some emails from the Greens and all these persons. But even we are able to produce these in recyclable paper. It's not a problem. For example, in our case, we can start with paper, produce the transistors using these metal oxides, because they are already, some of them belong to the intrinsic composition of the paper, zinc oxide and all these materials. And at the end, I can recycle everything, including the electronics, and build recyclable paper and make more transistors. So we can close the cycle. It's not in one direction. But of course, that's why also we are looking with vinegar, not only to the pinus and eucalyptus, but we are looking to these bacteria. And they are quite smart, believe. because they appear before us, and I guess they will stay after us. Yes.
So I would really like us to thank Professor Elvira, because
I will make
she made the
available.
she made the effort of, after the long trip, after losing a connecting flight, still being here and making sure that we have this talk. So thank you so much for
Okay,
this.
and I will make available the presentation if you
Okay,
wish
yes,
to,
yes,
and also
please.
you can send me an email if you want, or visit my laboratories. You are free to go there, especially the guys that are in Portugal.
Yeah. So a warm applause.
Okay, thank you.